Hello everyone, I am Dipak Chandrapal from the Department of Geological Sciences, Jadavpur University, Kolkata. I will be discussing about sulfur isotopes, its natural variations and fractionations during different geological processes. I will also touch upon some selected applications of sulfur isotope in understanding geological process. You know, sulfur is the 16th element in the periodic table and it is the 10th, 8th and 12th abundant element in the solar system, in the bulk earth and in the continental crust. It has 4 stable isotopes, sulfur 32, 33, 34 and 36. Amongst this, sulfur 32 is the most abundant isotope, which is about 95.02% in abundance, followed by sulfur 34, which is about 4.25% in abundance. And these 2 stable isotopes of sulfur 32 and 34 are most commonly used to understand the geological processes. One important thing about sulfur is that it occurs in multiple oxidation states starting from +6 in sulfate to -2 in H2s or HS minus, and there are several intermediate oxidation states. And as sulfur occurs in different oxidation states, it is stable in different geological environment starting geological environment including in the atmosphere, hydrosphere and biosphere. So, that is one reason why sulfur isotope is so important in understanding geological processes, and at the same time the sulfur isotope fractionations become very complex because of its occurrences in several oxidation states. So, before we get into the details of sulfur isotope studies, let us have some idea about some definitions related to sulfur isotope studies. Now, the first one is fractionation factor, which is known as alpha, and this alpha is defined as the ratio of the heavier by lighter isotope between 2 coexisting phases. Quite commonly, the isotopic composition of a phase is compared with respect to a standard or reference point, and that is expressed at delta 34. In case of sulfur, we call the delta 34S, which is actually the 34/32 sulfur ratio in a phase A minus 34/32 sulfur in a reference material divided by 34/32 S in the reference material, and these values are expressed in terms of parts per mil or parts per thousand. The reference material often used is Canyon Diablo triolite, which is a iron sulfide found in the Canyon Diablo meteorites in Arizona. However, recently this Canyon Diablo triolite has been replaced by VCDT, which is Vienna Canyon Diablo triolite. In case of 2 coexisting phases, the sulfur isotope ratio, differences between isotopic ratios of 2 samples are known as relative enrichment factor, and these relative enrichment factors, the fractionation factors, they are related by this different equations. Now, this fractionation factor alpha in most of the cases is close to 1, particularly when the fractionation is taking place at high temperature. So, therefore, if alpha tends to 1, then alpha minus 1 tends to 0, and when alpha minus tends to 0, then ln alpha tends to 0. Therefore, in such cases the equation can be actually expressed by or summarized as the relative enrichment factor can be rewritten as 10q ln alpha by replacing alpha minus 1 by ln alpha. Now, these alpha values are actually temperature dependent, and in isotopic fractionations, the temperature dependent alpha factors are often expressed as A by T square plus B by T plus C, where A, B and C are experimentally determined values. Now, let us have a look on the variations in the sulfur isotopic compositions in nature. Now, the variations in the sulfur isotopic composition in nature is expressed in the same way as that of the other isotopes. So, they are represented by the del 34S values. Now, here is a figure where the del 34S values are plotted in this axis, x axis, and this is the positive direction, this is the negative directions. There are few important things that you can see from this figure is that first of all the meteorites, the basic seals and the mid oceanic ridge basalts, all of them has values close to 0, whereas the modern seawater has a very restricted composition of around plus 20. So, it appears that these two samples or the reservoirs, they actually represent two n member compositions. And there are two more things which is to be noted. One is that the sulfide, the isotopic composition of the sulfides is often or almost always much less than that of the coexisting sulfates in different sulfides in the different sulfide deposits. Also, the volcanic gas or volcanic H2s, that has a negative value, whereas the volcanic SO2 has a positive del 34s value and higher values compared to the volcanic H2s. The sedimentary sulfide has a huge range covering almost the entire range of negative and positive values. Now, these extreme variations in the sulfur isotopic compositions indicates that there must be some processes which has resulted in the isotopic compositions or variations in the isotopic compositions. So, meteorite and modern seawater appears to be the two n member isotopic compositions, and maybe they are the two the sources, n member sources, from which the sulfur isotopes or the sulfur has been recycled to generate these isotopic variations in nature. There are several mechanisms by which sulfur isotope can fractionate in nature. Now, we know that the stable isotope fractionations take place due to these mass variations, or these isotopic fractionations are actually mass dependent. Besides the mass of the isotopes, there are other physical and chemical parameters, for example, temperature and the ionic radii and the charges of the isotopes, that also have important control on the fractionation processes. In fact, the chemical parameters control the bond strength of the isotopes with the anion or with the ions with which they are actually attached, and higher the bond strength or the stronger the bond, the heavier isotopes are usually preferred in the stronger bonds. For example, in case of sulfur isotopes, sulfate in SO4, sulfur oxygen bond is much stronger than H2S hydrogen and sulfur bond in H2S. Therefore, in case of sulfur isotope fractionation between sulfate and H2S, heavier isotope goes to sulfate compared to that of H2S. As I have said, there are different processes by which sulfur isotope fractionates in nature, but I have already mentioned that magmatic water or the magmatic source, they have a distinct isotopic composition and represent a n member isotopic composition. Similarly, seawater also represent a n member isotopic composition. So, I will talk about the isotopic fractionations during the magmatic processes as well as during the reduction of seawater sulfate. Now, during the process of partial melting of a rock, maybe in the mantle or the upper crust, the temperature is extremely high. So, the fractionation is expected to be negligible or there would be no fractionation, and when the minerals precipitate from this melt, again the temperature is very high. So, therefore, we will not expect any fractionation to take place between the mineral and the melt. However, when there is fluid saturation, that means with increasing crystallization, when the melt becomes saturated with fluid, then there is a chance of sulfur isotope fractionations. For example, at temperature higher than 400 degrees centigrade, H2S and sulfur dioxide dominate in a hydrothermal fluid. So, the total isotopic composition, that is delta 34S fluid, is equal to delta 34S of H2S into XH2S, where XH2S is the mole fraction of H2S, plus delta 34S SO2 into XH2S. So, clearly during these processes, the mole fractions or the mole ratio plays a very important role in the sulfur isotope fractionations. And if the sulfur in the melt occurs mainly in the form of HS minus or SH minus, and the species in the fluid is mainly H2S, the reduced species in the form of H2S, then the isotopic fractionation can be expressed by this relation. So, again, all these relations suggest that the isotopic composition would depend on the mole fractions of the species present in the fluid at that point of time. In this case, we are talking about two fluids, one is H2S dominated or H2S fluid, and the other one is sulfur dioxide fluid or sulfur dioxide species. Now, what will happen when a fluid is actually being released or exhaled from a magma. Here is a diagram where you can see the temperature versus log activity of oxygen with respect to this basaltic magma and the rhyolitic or dacitic magma. And note this solid line which is actually SO2 H2S boundary, above which SO2 is stable and below which H2S is stable. What you can see here is that basalt lies mostly below the SO2 H2S line, which means if a fluid is derived from a basaltic melt, it will be dominated by H2S, and as it is dominated by H2S, remember that in the melt the sulfur species occurs mostly as HS minus, and if the fluid is dominated by H2S, then fractionation would take place between H2S by SH minus or HS minus, but there is practically no fractionation between SH minus and HS minus. The reason is the bond strength of sulfur and hydrogen in H2S and sulfur and hydrogen in HS minus are very similar. So, practically no fractionation takes place at this point of time. In case of rhyolitic magma, large part of this magma or some of the magma lie above this SO2 H2S line, whereas some magma lies below the SO2 H2S line. Now, if the magma composition lies below the SO2 H2S line, that means if the melt is more reduced in nature, containing more of H2S, then the fluid which is being exhaled from this melt will behave in a similar fashion as that of the fluid which is coming out of a basaltic melt. However, if it lies above the SO2 H2S line, then the fluid which will be exsolving from that melt will be SO2 dominated. Now, the sulfur in the melt occurs as HS minus, whereas sulfur in the fluid occurs as SO2. Now, SO2 has a preference for the heavier isotopes, where HS minus has a preference for the lighter isotope compared to SO2. So, there is expected to be huge fractionation, but this will depend on important thing, which is the volume fraction of the fluid which is being generated. If a large volume of fluid is being generated at this point, then most of the sulfur that was occurring in the melt will go out in the fluid, and all the sulfur that was occurring in the melt will be transferred in the fluid. So, the fluid will carry the isotopic composition of the melt. So, there will not be any change in the isotopic composition of the fluid of the sulfur in the fluid. However, if the volume of that fluid is low, then the sulfur occurring in the melt will not be completely transferred to the fluid, and therefore, whatever sulfur dioxide occur in the fluid will have there will be a strong fractionation between the whatever sulfur dioxide present in the fluid and the HS minus in the melt. So, the SO2 in that case will be enriched in heavier isotope. So, the delta 34S of sulfur dioxide will be higher than the delta 34S of H2S or HS minus in the melt. During the precipitation of minerals, sulfide minerals from a hydrothermal fluid, as we have just discussed now, we will need H2S, because H2S reacts with the metals to form the sulfide minerals. So, it is important for us to understand what is the isotopic composition of H2S in a hydrothermal fluid derived from a magma. So, this is again a plot where between temperature versus log activity plot. Here, similar to the previous diagram, I have plotted this SO2 by H2S line, above which SO2 is stable, below which H2S is stable. Now, during the evolution of a fluid with decreasing temperature, the fluid may maintain its SO2 by H2S ratio, or the SO2 by H2S ratio may change by variable reactions. For example, if a SO2 H2S bearing fluid reacts with FeO or iron plus in the rock, then SO2 will be reduced to form H2S, and the SO2 H2S ratio will decrease. So, there are similar other reactions by which we can change the SO2 by H2S ratio. Now, if the fluid was initially in the H2S dominated field and it remains in the H2S dominated field, there will not be any fractionation with decreasing temperature, and even if there is a fractionation, that will be very little. However, if this fluid crosses the SO2 H2S line, then H2S will be gradually converted to sulfur dioxide or SO2, and as we know that sulfur dioxide prefers the heavier isotope, and as we generate more of SO2, then the heavier isotopes which are initially contained in H2S, that will be transferred to SO2. So, basically sulfur dioxide will snatch the heavier isotope from H2S, and this will result in a decreasing del 34S value of remaining H2S. Now, if the fluid lies initially in the sulfur dioxide dominated field, that is above this line, and if the SO2 H2S ratio does not change, then there will be fractionation with decreasing temperature. So, the H2S will be gradually be depleted in the heavier isotopes, because as the temperature decreases, we know the fractionation becomes more prominent. So, sulfur dioxide again will take away the heavier isotopes from H2S, and H2S will be gradually depleted in 34S, resulting in lower del 34S value. Now, if SO2 if the fluid crosses the SO2 H2S boundary and moves to H2S towards the H2S field, this means that some of the sulfur dioxide will be converted to H2S, and as the sulfur dioxide are being converted to H2S, the heavier isotopes which are stuck in sulfur dioxide will now be taken up by H2S. So, H2S will now keep on gathering more of sulfur 34, resulting increase in the del 34S value of the H2S in the fluid. And so, as we can see that the del 34S value of H2S will change depending on the initial fluid composition as well as how the fluid evolves during its decrease in the temperature, and this will be certainly reflected in the composition of the minerals that precipitate by interacting with this H2S. Now, let us have a look on how the fractionation takes place during the reduction of seawater sulfate to form H2S. Seawater sulfate can be reduced by two major processes. One is the bacterial sulfate reduction, which is BSR, and the other one is thermochemical sulfate reduction, or TSR. And this bacterial sulfate reduction actually takes place below the sediment water interface, where the environment is anoxygenic, and the bacteria like desulfovibrio or desulfuricans is one of the common agent which helps in the fractionation or bacteriogenic fractionation of seawater sulfate during its reduction. The CH2O shown here actually represent the generic organic matter. Now, the fractionation of sulfur isotope during seawater sulfate reduction by bacteria will depend on whether the system was open or closed. Now, if the system is closed, for example, if the sediment water interface lying below the water table is somehow isolated from the seawater, then that will not be replenished by seawater sulfate. So, the system will be close to sulfate. Now, if there is no mechanism to consume the H2S which has been produced by the reduction of seawater sulfate, so H2S will not be taken up by any other things, and the common mechanism by which H2S can be actually consumed is the reaction of H2S with the metals, forming the metal sulfides, or the loss of H2S in the overlying water column, or formation of some organometallic complexes or organic complexes. So, if there is no such mechanism is present, then H2S will not be consumed and the system will be close to both SO4 and H2S, and in this case very soon the H2S and SO4 will reach to an equilibrium. So, this will be an equilibrium fractionation process, and the isotopic composition of H2S will depend largely on the H2S by SO4 ratio, and the isotopic composition will be highly skewed, and the sulfides precipitating from such a solution will have a very restricted isotopic composition. Now, in other case where, for example, the system is close to seawater seawater sulfate. That means, seawater sulfate is not being able to replenish the zone of seawater sulfate reduction below the water table, whereas the H2s is being consumed by the processes just I have mentioned. So, in this case what will happen is that in the early stage the H2s produced will have a strongly negative value, because there is an extreme fractionation between SO4 and H2s, as I have just already mentioned that sulfate takes in the heavier isotope and sulfides takes in the lighter isotope. So, the whole process can be expressed by Rayleigh fractionation, in which the early form sulfides will have a strongly negative value, but as the process goes on, the residual sulfate will be extremely enriched in heavier isotopes, and the later sulfides which will precipitate, or the later H2s which will be produced from this highly enriched sulfate will also have a positive values, delta 34S values. So, the minerals which will precipitate from this H2s at a later stage will have a positive delta 34S value, and this will not be as skewed as in case of closed system sulfur isotope fractionation or sulfur isotope reduction to sulfides. And there is another process which is known as thermochemical sulfate reduction. In fact, there are many geological processes where, or there are many old deposits where there are evidence that bacteria did not operate in those cases. In fact, this sulfate reducing bacteria that operate mostly in the temperature range of 20 to 40 degrees centigrade, but there are many deposits which form at a much higher temperature where bacteria cannot survive. So, sulfate reduction in those cases takes place by inorganic processes, but in the presence of organisms which just help in the reduction of the sulfates. And in many cases it is observed that this reduction process operates with the formation of an intermediate sulfur species. For example, it has formed sulfur here, and this sulfur further in the presence of organic matters can convert it to H2s. So, it is not a direct reduction of sulfate to sulfide, it is a reduction of sulfate to sulfide through an intermediate stage of maybe sulfur or some other intermediate states of species of sulfur. So, as there are intermediate species formations, so these processes do not result in extensive fractionation of sulfur isotopes during the reduction process. In some cases, seawater sulfate also gets reduced when it reacts with iron plus 2 in fayalite or magnetite during the journey of the seawater through the cracks in the mid-oceanic ridges. There are a lot of mafic rocks where there are plenty of fayalites and magnetites. When the seawater passes through these mafic rocks, they can interact with iron in plus 2 oxidation state and can be reduced to form H2s. Again, these sort of processes are usually reach to equilibrium very often or very soon, and therefore, not much of fractionation is seen in thermochemical sulfate reductions, unlike the bacteriogenic sulfate reduction. Now, let us discuss about some of the applications of sulfur isotopes. So, I will first talk about the mass independent fractionation and its implication in early atmospheric oxygenations. We have discussed that sulfur isotope fractionations are usually mass dependent. Now, if the fractionations are mass dependent, then there should have some relation between delta 33S and delta 34S. Now, delta 33S is actually the similar thing as that of the delta 34S. The only difference is that in the place of 34 sulfur, 33 sulfur is used, and here 33 by 32 sulfur ratio is used. Here we use 34 by 32 sulfur ratio, and here we use 36 by 32 sulfur ratio. Now, if there is MIF, then the delta 33S value should be about half that of delta 34S value, because the mass difference between 32 and 33 is 1, whereas the mass difference between 34 and 32 is 2. So, exactly it should happen that delta 33S value should be about 0.515 into delta 34S, whereas the delta 36S should be equal to 1.90 into delta 34S. But this is not the case in many geological environments. Ideally, as I have just said, ideally if there is MIF, then the samples in a plot of delta 34S versus delta 33S, the samples should plot on a linear array. This array actually define a line which is delta 33S is equal to 0.514 into delta 34S, and this linear array is known as mass dependent fractionation line. However, in many Archean samples, it is observed that the samples the samples in the similar plot, they do not fall on this linear array, or they do not plot on the mass dependent fractionation line, they plot on the either side of this MFL or the mass fractionation line, mass dependent fractionation line. So, there must be a reason behind this. Now, what is the quantum of these sort of fractionations? The quantum of the fractionations are actually expressed by a cap delta 33S and cap delta 36S. Now, what cap delta 33S is? This is the difference between the delta 33S which is obtained from the sample minus 0.515 into delta 34S which is actually expected for a mass dependent fractionations. Similarly, cap delta 36S is expressed as delta 36S minus 1.90 into delta 34S. There are some recent studies in which it is observed that in rocks which are older than 2400 million years, there the cap delta 33S which should be actually 0 if there is mass dependent fractionation, this cap delta 33S values, they fluctuate and they have a huge negative and positive value starting from about 2.0 to minus 2. So, clearly these samples are not the results of mass dependent fractionation. Now, from the 2400 to about 2000 million years, we see some little bit of fractionations. The values they straddle around this 0 value, but still there are some variations in the delta 33S value. But in rocks younger than 2000 million years, almost all the samples and there are in fact more samples to show this, that they fall on this delta 33S is equal to 0 line. So, what is the possible explanation for this? Now, up till now there has been only one explanation. In experimental studies, it has been observed that the ultraviolet ray, when it interacts with sulfur dioxide, it produces sulfur monoxide and oxygen, and the sulfur monoxide can again break into sulfur and oxygen. Now, during this photolysis of sulfur dioxide by ultraviolet ray having a wavelength of 190 to 220 nanometer, this sulfur dioxide attains a cap delta 33S value less than 0, whereas the sulfur monoxide that attains a cap delta 33S value of more than 0. So, this is the only experiment in which it has been observed, it has been shown that ultraviolet rays can do the job by photolysis of sulfur dioxide, producing two different cap delta 33S values, one for sulfur dioxide and another for sulfur monoxide. Now, if the sulfur dioxide in the atmosphere, if there was abundant sulfur dioxide in the atmosphere, in fact, in the modern day sulfur dioxide are being added to the atmosphere through the magmatic activity, volcanic activities. So, there is enough reason to believe that sulfur dioxide was lofted to the atmosphere in the early earth as well, and if there was sulfur dioxide, then if and this sulfur dioxide might have interacted with the ultraviolet ray to form these sort of variations, wherein the sulfur dioxide attains a negative value and the sulfur monoxide attains a positive value. Now, if these sort of variations took place due to the ultraviolet ray, after the formation of sulfur dioxide, this sulfur dioxide could have combined with the oxygen to form sulphite, and this sulphite after combining with H2O would have formed H2SO4. And once this H2SO4 is formed, that will come down with the rain and become a part of the hydrosphere. And in the hydrosphere, these sulfates or the sulfidic acids or whatever form they are, they can form these sulfate minerals, for example, barite, whereas the sulfur produced or the sulfur particles which are produced by these photolysis reactions, this particulate sulfur again may come down to the earth's surface and be a part of the sulfide minerals. So, the sulfide minerals are expected to carry the positive values, whereas the sulfates which are formed from the sulfur dioxide are expected to carry a negative cap delta 33S value. Now, the question is, so what is the implication of this? What is the implication or interpretation of this sort of observations? So, it is important to note that the ultraviolet ray having a wavelength of 190 to 220 nanometer is absorbed by largely by ozone and partly by molecular oxygen. So, if this ultraviolet ray has to be present in the early atmosphere, then the ozone must be absent in the early atmosphere, because the presence of ozone will absorb this ultraviolet ray and there will not be any ultraviolet ray available to photolysis this SO2 and cause this MIF signature. So, the ozone must have been absent, ozone layer must have been absent during that time, and we know that ozone is formed by molecular oxygen, and if ozone has to be absent, molecular oxygen has to be absent in the early atmosphere. So, this is a strong indication of the early anoxic or low oxygenation oxygenated atmosphere in the early Archean. In fact, there are several parallel lines of evidences which indicates the early atmosphere was anoxic. And the anoxic atmosphere which prevailed up to almost 2400, then the atmosphere started becoming oxygenated, and from about 2000 million years the atmosphere became almost as oxygenated as we see it today. So, this is how the sulfur isotope studies can help us to understand the early oxygenation in the atmosphere, and there are another applications. For example, the isotopes can be applied to understand hydrothermal ore deposits. In fact, some of the questions that we asked in understanding hydrothermal ore deposit is that what is the temperature of mineral precipitation. So, let us have a look on this figure, which is the 10 cube ln alpha of the different species with respect to H2s, and this is variations with temperatures. So, for example, this line means that the alpha or the fractionation between sulfate and H2s dependent on the temperature. Similarly, this line indicates the fractionation, the dependence of the fractionation factor on temperature of lead S PBS with respect to H2s. Now, if we have the sulfide minerals and the coexisting H2s, so from these fractionation factors we can directly find out the temperature, but in a mineral deposit we do not have the H2s present, we only have the sulfide minerals. So, to find out the temperature of the sulfide mineral crystallization, we need to know the fractionation factors between two sulfide minerals, for example, galena, PBS and for example, ZNS. Now, it is not a very difficult one to do this. This can be exercised, like we know the alpha values, fractionation factors of say galena versus H2s, and we also know the fractionation factors of sphalerite versus H2s. So, from these galena versus H2s fractionation factors, we can find out the delta lead-S PBS values, and similarly from delta ZNS value, we can also obtain express the delta ZNS value in terms of 10 q ln alpha in ZNS versus H2s, and doing this exercise we can finally actually find out the delta ZNS minus delta PBS value in terms of alpha ZNS versus H2s and alpha PBS versus H2s. Now, these are already experimentally determined. We know the temperature dependence, as I have already shown. this is ZnS versus H2s. So, we know this temperature dependence of ZnS versus H2s, and this PBS versus H2s, and we also know this PBS versus H2s from these figures. So, these are all known, and these values we can obtain from the samples we are studying. So, using these equations we can find out the temperature dependent fractionation factor of the different sulfide minerals, and from that we can find out the temperature. Now, the next application is the composition of the fluids that precipitated the minerals. Now, the isotopic compositions of H2s and SO4 in a fluid can be obtained from the fractionation factors. For example, if I know the isotopic composition of pyrite, and if I know the fractionation factor between pyrite and H2s, then knowing the temperature, the isotopic composition of H2s can be obtained. Similarly, the isotopic composition of SO4 in the fluid can be obtained, but please remember that just getting the isotopic composition of H2s in the fluid during the precipitation of the mineral, or for that matter getting the isotopic composition of sulfate in the fluid during its precipitation of the sulfide minerals, will not give us the isotopic composition of the overall fluid. So, what we need in that case is that the molar proportions of H2s and SO4, and also know the pH values and the oxygen or sulfur fugacity during the precipitation of sulfide minerals. There are different ways to know that, but it is not a very easy task, but still we can find out these values, particularly the molar ratios of different H2s versus SO4. For example, in the absence of for example, if the mineralization, in the mineralization we find that pyrrhotite is present as a stable phase and the temperature is less than 500 degrees centigrade, then in such a situation H2s is expected to be the main or practically the only sulfur species in the fluid, and in those cases del 34S of the fluid would be actually equal to the del 34S delta 34S of the fluid will be actually the delta 34S of the H2s that we can obtain from the fractionation factors and the delta 34S values of the sulfide minerals. Now, there is another applications, I will just complete my presentations with this another important applications. Here the delta 34S of H2s is plotted against the delta 34S of sulfate, rather the coexisting sulfate. Now, if these two minerals, if the sulfides and the sulfate minerals, they precipitated from a equilibrium state or they were in equilibrium, then they should fall along a particular line in this XY plot. For example, if the fluid had only H2s, that means the sulfate was 0, that is the fluid was completely composed of H2s, then the values of delta 34S H2s, that means the sulfides, by H2s I mean the sulfides here, and SO4 I mean the sulfate, these are the sulfides and these are the sulfates. So, they will fall along this line, whereas if the fluid contain only sulfate and no H2s, then they will be plotted along this line. For any other compositions or for any other sulfate by sulfite ratio, the values will be plotted along some lines in between these two horizontal and vertical lines. And as an example, this is the line which is a 45-degree line along which this SO4 by H2S ratio is actually 1. When these lines are extended to the 0 fractionation line, that means SO4 minus H2S cap delta SO4 minus H2S is equal to 0. So, when these values are extended to this line, the intersection point gives the isotopic composition of the fluid. So, now to summarize, there are extreme variability in the sulfur isotopic compositions of natural materials. One of the major reasons behind this is the stability of sulfur or the occurrence of sulfur in multiple oxidation state, which controls the bond strength, and the bond strength controls the different fractionation processes involving sulfur. On top of it, sulfur isotopic fractionations are also controlled by biotic and abiotic processes. So, the resultants are resulting in different compositions of sulfur isotopes in nature. However, still there are two major sources or the two major reservoirs of sulfur having distinctive isotopic composition. One is seawater and the other one is magma or the meteorites. And using these two end member compositions, we can understand the sulfur isotopic variations in nature, and sulfur isotopes can be very well used to understand different geological processes. One of the most important application of sulfur isotope is to understand the early atmospheric evolutions, the oxygenation of the early atmosphere, and most of the studies on the understanding of early atmospheric evolution involving isotopes, rather stable isotopes, has been done including sulfur isotopes, although there are some studies that include oxygen studies, oxygen stable isotope studies to understand the early oxygenation environment or early oxygenation in the atmosphere. Now, sulfur isotopes are very useful to understand the ore forming processes, particularly the hydrothermal processes, but few things we need to remember. First of all, we can get the temperature, we can get the fluid composition. However, this fluid composition is the composition of the fluid from which the mineral precipitates. It does not necessarily is the same fluid which has been derived from the source, because we have discussed and described that during the process of fluid evolution, for example, in case of magmatic fluid, even if the original melt had the 0 delta 34S value, that can be modified during the evolution of the hydrothermal solutions. So, just having the isotopic composition of the fluid, we should not comment on the source of the fluid immediately. To do so, we need to have some idea about the geology of those areas, evolutionary history and geochemistry of the materials that we are working on. So, with that, I thank you very much.